Hello, game theorists. Today we are in Chapter 7, looking at simultaneous move games with mixed strategies. We talked about mixed strategies a little bit earlier on, but now we're going to go into more depth. So, you know, recall a mixed strategy is one where the players randomize. So the example you're probably familiar with is rock, paper, scissors. You don't want to always play rock or always play scissors. It's best to be a bit unpredictable and to randomize. So you probably figured out as a kid very early on that if you're playing rock, paper, scissors, you want to play each one, rock, paper, or scissors, with probability 1/3 each to be totally unpredictable. We'll actually prove later on in this chapter that this was the best solution. So here's an example. So we'll have two players, and our row player can pick either A or B. Column player can play X or Y. Let's say our row player is Ethan, and our column player is Richard. Two of my students from last semester. Payoffs are as follows. So recall from before, the row player's payoffs always come first. So over here we have -5, 5. That means Ethan will get the -5 and Richard will get the +5. So the first step for our analysis is try to find a Nash equilibrium, so do your best response analysis. Go ahead and pause the video here and try your best response analysis and see what you come up with. When you're ready, press play. All right, I'll assume you have taken a stab at it. So if you did things right, you'll find there is no pure strategy Nash equilibrium. Remember, pure strategy just meant that there is no randomization. So if Ethan plays A, Richard's best response is to play Y and get 5 because that's better than getting -50. If Ethan plays B, Richard wants to play X and get 10 instead of getting -20. If Richard plays X, Ethan's best response is to play A and get 50 instead of -10. If Richard picks Y, Ethan wants to go for B. So there's no cell here that has both payoffs underlined. So I'll say no pure strategy Nash equilibrium. Now, there still is a Nash equilibrium, it's just not involving pure strategy. The Nash equilibrium will involve randomization. So let's say that Ethan's going to play A with probability P. That means he plays B with probability 1 minus P. So now I'll find Richard's expected payoff from each of his strategies. So use pi for payoff. I'll use pi r to be Richard's payoff. This is going to be Richard's payoff given that he's playing X. So if Ethan plays A, Richard gets the minus 50. Remember, Richard is our column player, and the column player's payoffs always come second. The probability of Ethan playing A is going to be P. Now, if Ethan plays B, Richard gets positive 10. The likelihood of Ethan playing B is going to be 1 minus P. So let's go and expand that. We get minus 50P plus 10 minus 10P. That works out to 10 minus 60P. Next step, let's find Richard's expected payoff from playing Y. So if Ethan plays A, Richard gets 5. The probability of Ethan playing A is P. If Ethan plays B, Richard gets negative 20. The probability of Ethan playing B is 1 minus P. So you get 5P minus 20 plus 20P. That comes out to minus 20 plus 25P. So we found the expected payoffs for each of Richard's strategies. What he expects to get if he plays X, what he expects to get if he plays Y. So we can now determine what Richard would want to play. So if the expected payoff from playing X was bigger than expected payoff from playing Y, what's Richard going to do? He's always going to play X. So the players want to maximize their expected payoffs. So if one's just always bigger than the other, you want to go for the bigger one. Now we know, though, if Richard always plays X, then Ethan always wants to play A. But if Ethan, because playing A gives him 50 with certainty. If he randomizes, he could get 50 sometimes and minus 10 the other time. It's better to always get plus 50. So this is true. Richard always plays X. However, if Richard always plays X, Ethan's going to always want to play A. Ethan's not going to randomize. So if that happens, then we're not going to be able to find any mixed strategy, no randomization in what the players do. Remember, we already said there's no pure strategy in Nash equilibrium. There's no cell here had two underlines. So the only case was Nash equilibrium is when the players randomize. We just established, though, if this is true, then the players don't randomize. So you can rule out that case. This case means there's not going to be a Nash equilibrium. Let's look at another possibility. Let's say Richard's expected payoff from plane Y is always bigger than expected payoff from plane X. Well, again, Richard always wants to maximize his expected payoff. So if one's always bigger, you go for the bigger one. Now, if Richard always is going to play Y every single time, what does Ethan want to do in response? Let's see, if Richard plays Y, Ethan could get -5 from plane A. Alternatively, he could get +20 from plane B. So in that case, actually, Ethan will always want to play B. Now, Ethan could randomize, but that means getting +20 only some of the time. We better get +20 all the time. So Ethan's going to stop randomizing. He'll start playing B every single time in response. So again, no randomization. So that's another case you can rule out in your search for Nash equilibria with randomization or mixed strategy Nash equilibrium. So we can't have X being better than Y, and we can't have Y being better than X. We also rule out that case as well. That leaves us with only one remaining possibility. In a Nash equilibrium with mixed strategies, these expected payoffs must be equal. So, in other words, when Ethan's picking his mixture, when he's picking his probabilities, he has to do so in a way that leaves Richard indifferent. If Richard's indifferent, then Richard would be willing to randomize. If X and Y give him the same expected payoff, you can play them both with different probabilities. On the other hand, if one is always better, then you play one that's better. So we really ruled out those cases. You have to have them be equal so that Richard is willing to randomize. So once Richard starts randomizing, he's making himself unpredictable. Ethan is then also justified in making himself unpredictable as well. So that's a very important concept. It's called the opponent's indifference property. So Ethan picks P. He's picking his probabilities to make Richard indifferent. And once again, if if the strategies did not have the same expected payoff, then you want to always go for the one that's better. It's only when they're equal that randomization makes sense. So with that in mind, let's go through and solve this game. So we said that we had to have Richard's expected value from plane X equal to expected value from plane Y. We also established that the expected payoff from X was 10 minus 60p. Expected payoff from Y was minus 20 plus 25p. One equation, one unknown. This shouldn't be too bad. So I'll add 20 to both sides, so I get 30 over here. I'll add 60p to both sides, so I get 85p. Let's divide both sides by 85, so I get 30 over 85 equals p. That can simplify, so 5 fits into 36 times, and 5 fits into 85, I believe, 17 times. So that's how Ethan wants to randomize. So we said Ethan plays A with probability P back here. And we just solved that P should be 6/17. Now we're not done yet. We also have to find out how does Richard want to randomize. So the next step is to find how Richard is going to randomize his strategy. Let's say he plays X with probability R. That means he plays Y with probability 1 minus R. So we use the same technique to find what R should be for Richard. We're going to use the opponent's indifference property. Richard has to pick R in a way that's going to make Ethan indifferent between A and B. Same idea as last time. So if you picked R in a way that made Ethan not indifferent between A and B, then Ethan always plays the one that's better. You got to make them equal so Ethan is willing to randomize. So we'll calculate Ethan's expected payoffs. So the payoff for Ethan from playing A, well, sometimes when he plays A, he gets 50. That happens with probability R. Now, if Richard plays Y, then Ethan gets -5. The probability of that happening is 1 minus R. So let's go and expand that. 50R minus 5 plus 5R. That's going to be 55R minus 5. Now let's find Ethan's expected payoff from playing B. So he gets -10 with probability R. He gets +20 with probability 1 minus R. So you have -10R plus 20 minus 20R. That simplifies to 20 minus, combine these guys, minus 30R. So like I was saying, you have to make Ethan indifferent between these payoffs to get him to randomize. If this was always bigger than that, he's always going to play A and get this. If this were always bigger, then he'd always play B and get the bigger payoff. So the only way it makes sense to make Ethan randomize is if these are equal. So let's do some rearranging. I'll put the 30 over here, so I get 85R. The 5 goes over there, so we get 25. Then we get R equals 25 over 85. To simplify, so both divisible by 5, so we get 5 over 17. So, to be clear though, don't write your answer as R equals 5/17 and P equals 6/17. That's because we don't know which one's P and which one's R. Does P mean probability of A or probability of B? Does R mean probability of X or probability of Y? So just write it out more formally like this. So the Nash equilibrium is, we said that Ethan plays A with probability P. We said P was 6 over 17. So A with prob 6/17. That means he plays B with probability 11/17. We said Richard plays X with probability R. R is 5/17. That means he plays Y with probability 1 minus R. That's 12 over 17. And that's your Nash equilibrium. So that wraps up that example. Be sure to tune in for our next episode and learn more about mixed strategies.